Hello, friends. Have you ever wondered what actually happens inside your computer's memory the moment you call a function in C? Where do your local variables go? How does the program know exactly where to come back to after the function finishes? The answer is something called stack memory, and it works on a beautifully simple rule called LIFO, which stands for last in, first out. In this video, we're going to break down what stack memory is, how it powers every single function call you write, and why understanding it will instantly make you a better programmer. Let's dive in. Alright, before we get into memory, let's understand LIFO with something you've seen 1,000 times, a stack of plates. When you wash a plate, where do you put it? Right on top of the stack. And when someone needs a plate, which one do they grab? Also from the top. The plate you put down last is the one that comes off first. That's it. That's LIFO, last in, first out. Now look at the right side. Stack memory works exactly the same way. It's a region of memory where data gets added on top. We call that a push, and removed from the top. We call that a pop. You can't reach in and grab something from the middle. Only the top item is accessible at any given moment. This might sound like a strange limitation, but as you'll see in a moment, it's actually the perfect design for handling something every program does constantly, calling functions. Now let's zoom in. When you call a function in C, let's say main, the program doesn't just throw random data onto the stack. It creates a neat, organized package called a stack frame. Think of a stack frame as a little box that belongs to one specific function call. And inside that box, 4 important things get stored. First, the local variables. Any variable you declare inside the function, like int x equals 10, lives right here. Second, the function parameters, the values you passed in when you called the function. Third, the return address. This is crucial. It's basically a bookmark that says, hey, when this function is done, jump back to this exact line in the code that called me. Without this, your program would have no idea where to continue. And fourth, the saved registers, small pieces of CPU state that need to be preserved while the function runs. So every function call gets its own private little box on the stack. And here's where it gets really interesting. What happens when one function calls another? That's where LIFO truly shines. Alright, let me show you how this actually plays out when your program runs. Step 1. Your program starts. The main function gets its own stack frame at the bottom of the stack. Simple enough. Step 2. Inside main, you call another function. Let's say add 2, 3. The moment that call happens, a brand new stack frame for add gets pushed right on top of main's frame. It carries its own parameters, its own local variables, and its own return address pointing back into main. While add is running, it sits at the top of the stack, and that's the only frame the CPU is actively working with. Step 3. Once add finishes its work and returns the value 5, its entire stack frame gets popped off, instantly gone. The CPU reads that return address we talked about, jumps right back to where main left off, and main continues like nothing happened. Here's the analogy that makes this click. Think about how the back button works in Chrome. Every page you visit gets pushed onto a history stack. When you hit back, the most recent page gets popped off, and you return to the previous one. Last in, first out. That's exactly how function calls work in memory. Now what if a function calls another function, which calls another, which calls another? Let's see what that looks like. Now look at this. In real programs, functions almost never run alone. They call other functions, which call other functions, and the chain can go pretty deep. Let's say main calls greet. While greet is running, it calls format name, and format name calls to upper to convert the name to uppercase. So we now have 4 function calls active at the same time. Look at the stack. Every single one of those calls has its own frame, neatly stacked on top of each other in the exact order they were called. Main is at the bottom because it started first. To upper is at the top because it was called most recently, and it's the one currently running. Now here's the elegant part. When to upper finishes, its frame pops off, and control returns to format name. When format name finishes, its frame pops off, and control returns to greet. And so on, all the way back down to main. Each function quietly resumes from exactly where it paused, because that return address was waiting in its frame the whole time. This is why LIFO is the perfect design for function calls. The function that was called most recently is always the one that needs to finish first before anything above it on the call chain can continue. The stack enforces that order automatically. But this raises a question. If every function call adds a new frame, what happens if the stack just keeps growing and never stops? Great question. The stack isn't infinite. Your operating system gives each program a fixed chunk of memory for its stack, usually around 1 or 2 megabytes. That's plenty for normal use, but it absolutely has a ceiling. Now look at this code. We have a function countdown that calls itself, and calls itself, and calls itself, with no condition to ever stop. This is called infinite recursion, and it's a classic bug. Every single one of those calls pushes a brand new stack frame. The stack keeps growing and growing and growing. And the moment it crosses that limit, boom, your program crashes with the famous error, Stack Overflow. You've probably even heard of the website Stack Overflow. Yes, it's literally named after this exact error. That's how iconic this bug is in programming culture. The fix is simple in concept. Every recursive function needs a base case, a condition that stops the recursion at some point so frames can start popping off instead of just piling up forever. So the stack is fast, organized, and automatic, but it's also limited. And that limit is something every programmer needs to respect. Alright, let's quickly tie everything together. Stack memory follows LIFO, last in, first out. Every function call you make gets its own neat little package called a stack frame, holding its local variables, parameters, and a return address that knows exactly where to jump back to when the function is done. Functions stack up as they call each other, and they pop off in reverse order as they finish, automatically, perfectly, every single time. But the stack has a ceiling. Push too many frames, usually through runaway recursion, and you'll hit the dreaded stack overflow. Once you really understand this, a lot of things in programming start to make sense. Why local variables disappear after a function ends, why recursion has limits, even why debuggers can show you a call stack when your program crashes. If this video helped the concept click, do hit that like button, and subscribe to Webronaq for more videos that break down the ideas behind the code. I'll see you in the next one.